Um, yeah, I guess I'm audible. So yeah, thanks to the organizers for putting together the in-house, and it's very nice to sort of speak to many people from ICTS. So what I'm going to talk about today is resonances on the way towards understanding the many-body localized phase. I understand that this is the last talk of in-house, and I am sort of the obstacle between everyone of you and a nice dinner. So I'll try to keep it rather short. Okay, so this is work done with Sam Garrett and John Chalker. Sam Garrett used to be John Chalker's PhD student, and now he has moved on to Berkeley, and we still work together. But before I sort of get into this idea of resonances and the many-body localized phase and try to sort of explain what essentially is the crux of a picture like this, let me say a few words about why do we care about many-body localization. I'm sure many of you have heard it for so many times that you don't want to hear it again, but nevertheless, for people who have not heard about many-body localization, let me say just one thing, that there are essentially two sort of somewhat complementary but equally important and fundamental ways in which we can understand why understanding this physics is important. And it all sort of started off in 1958 by, it was also started off in 1958 by Philip Anderson, when he showed that if you have sort of non-interacting quantum particles hopping around on a disordered lattice, they can actually localize exponentially. And this was sort of extremely different from the kind of block waves like picture that people were used to back then. And then, of course, Sir Neville Morton, one of his co-workers, came together and showed that if you are in one dimension, one spatial dimension, or in two spatial dimensions, an infinitesimal amount of disorder is enough to exponentially localize your eigenstates. Now, while that was sort of a huge thing, there was a natural question that, in real life, quantum systems or any sort of systems are not non-interacting, they interact. And then there was this question of what is the fate of localization in the presence of interactions between these quantum particles? And it might have been thought that it's a rather simple question. It's just sort of the next obvious step, that what happens when you put interactions, and you'll be able to answer this question very easily. But this is a topic that's still going on since a few decades now. And in the more recent past, there has been a lot of excitement about this phase for reasons I'll come to in a minute. But the essential question here is that, is this MBL phase a genuine phase of quantum matter which is stable to interactions? Now, why has this sort of although this has been going on since many, many years, why are people suddenly, or not suddenly, but why are people so interested in it since the last 10 years or so? And that is because there has been a lot of progress in understanding how isolated quantum systems sort of behave. And there is this idea that if a system is many-body localized, then very loosely speaking, different parts of the system do not communicate efficiently with each other. And if they fail to do so, then if I look at any sort of subsystem here, then the rest of the system fails to act as a bath, which is the mechanism by which isolated quantum systems thermalize, and we sort of all understand how it all comes together with equilibrium statistical mechanics and thermodynamics. So if the many-body localized phase does exist, then we would have sort of discovered a sort of robust class of systems that fail to thermalize. And when I say they fail to thermalize, I mean that the expectation values of local observables are not given by standard statistical mechanical ensembles like Gibbs, for example. And that basically is raises quite a number of fundamental questions, because then these MBL systems fall outside the paradigm of conventional statistical mechanics and thermodynamics. So now there has been a lot of evidence, mostly numerical and somewhat experimental, that this phase does exist in one spatial dimension. There is some evidence that it might exist in 2D, but that's highly debatable. And in 3D, we really don't know anything. One of the sort of major obstacles, technically speaking, is that these are quantum systems which have disorder, which have interactions, and we are really far out of equilibrium. We are not close to the ground state. We are sort of talking about energy densities which are or rather energies which are extensive in the system size. So we are really in the middle of the spectrum of this many-body system. And all sorts of techniques that we learn for many-body theory or many-body condensed matter systems, they don't really work for these systems. So you really have to, you're really pushed into a corner where you are not able to use the host of analytical methods that had been developed over the last many years. Numerical calculations are rather difficult because of this exponentially growing Hilbert space dimensions. So that's one of the sort of, these are some of the challenges that this field is facing. But nevertheless, some of us decided to push on and we said that, okay, this phase definitely is worth understanding. And let's see how far can we get towards understanding this phase. So the simplest, or in starting off with a very naive view, is to say that since the system is many-body localized, then it should have a description in terms of some integrals of motion which are local. So basically what we are saying is that there are some degrees of freedom in the system emergent which do not evolve in time, in the sense that they commute with your Hamiltonian or with the generator of your time evolution, and they have to be local. So then, basically, this is a statement about saying that you can have some operators, I'll call them tau zi, which basically are, or whose support is exponentially localized on some sort of sites. And then we call them local integrals of motion. And then these are basically exponentially dressed versions of physically localized operators. And then we say that, well, because all of this, these operators have to commute with the Hamiltonian, it means that the Hamiltonian of the system should have a representation of this form where it only has the tau z operators. And then to preserve the locality of the system, we say that this, these couplings basically decay exponentially with the distance. Now, this is nothing but sort of a slightly fancy and elaborate way of saying that the MBL phases are perturbatively connected to the Anderson localized phases. Okay, so far so good, and there is a lot of value to this construction because this does explain a lot of a lot about MBL systems. For example, the absence of DC transport, the logarithmic growth of entanglement entropy, bipartite entanglement entropy, and so on. But how good is this description? And this is obviously a sort of, it's a very phenomenological description, and one ought to put it to a test. So one can then say that, okay, DC transport, the absence of DC transport is indeed explained by this theory, but what about the universal low frequency response? And one of the sort of common things that we want to compute is something like a spectral function where we take a local operator, we compute its off-diagonal matrix element in the eigenbasis, and we say that, how does it behave as a function of omega, where omega is the energy difference. So basically, the idea is that if this MBL phase was perturbatively connected to the Anderson localized phase, and imagine this sigma z was my localization axis, then we would have said that, well, we expect this SZ spectral function to be vanishingly small because most of my eigenstates look very much like sigma z product states. So the off-diagonal matrix elements would be rather small. And we would expect this Sx of omega to be sort of, it should have some finite contribution. It should probably mirror the disordered distribution because, again, if my eigenstates are close to sigma z product states, I hit it with a sigma x operator, it flips a spin, and the energy cost, therefore, is basically whatever is the local disorder distribution. So this is the expectation coming from the picture based on local integrals of motion. So we put it to test, and we see that it fails because the low frequency response is actually, first of all, in blue, I have the SZ spectral function, and in orange, I have the Sx spectral function. And what we see is that it actually has a power law in omega. This exponent does depend on the disorder strength or what value of the parameters I put in my system. But more importantly, it does not do this. So then you take another step back and say that, well, is this even a good approximation that the matrix elements of sigma z should be quite small? And then we said, okay, let's then test that. And what we actually find is, suppose I define this capital Z as the off-diagonal matrix element of tau z or sigma z. And I'll come to this D quantity in a minute, but this is the distribution of this matrix element Z. And what we actually find is that it actually has a long power, it has a power law tail. Of course, these are bounded distributions because Z cannot be larger than 1, but it has a -3/2 power law. And then, this sort of begins to sort of concern you a bit because, something else is going on. So then we say that let's actually define something which we call a depolarization for reasons I'm not going to get into. But imagine I take a particular eigenstate n, and I sum this quantity over all m not equal to n. And I look at the distribution of this quantity. And what we actually find is that the tails of the distributions for both Z and D match very well with each other. So this gives you an indication that in this particular sum, there is, order 1 term, or, in sort of loosely speaking, there is one term which dominates this particular sum. And this sort of gives you an indication that what we thought of as the eigenstates of the system, namely these local or these Liom configurations, they actually pairwise resonate. And this is sort of a new phenomenology that we need to put into our theory in a controlled fashion. So the idea is that there are pairwise local resonances between Liom configurations. Okay, so then the next question is that how do we actually go about constructing a theory for these resonances? Because the fact that there are these long power law tails mean that something non-perturbative is going on. So for that, we go back to something that Dyson had originally thought about, which is to take a random walk through the ensemble. We call it parametric level dynamics. So we take our Hamiltonian and we put a random local perturbation, which allows us to walk through the ensemble of disorder realizations. If you're working with some sort of a flow case system or some sort of a random circuit, then you work with unitaries. And in that case, this is how you generate this fictitious dynamics. And what we find is that every time there is an avoided crossing, so we track states which have particular Liom configurations, we find that this off-diagonal expectation or off-diagonal matrix element Z shows a large peak. And what that essentially means is that these Liom configurations are indeed resonating with each other. And at these resonances, the eigenstates are losing their Liom characters. Now, of course, there is some, there's a statistics of this, and there's a statistical mechanical problem here to solve, which is basically the statistical mechanics of a gas of eigenvalues which repel each other, and the repulsion is set by matrix elements. But it's a bit more complicated than that because these matrix elements are actually correlated with the spectral properties. So what we really want is the joint distribution of this Z and omega near the resonances. That's the quantity that we want to calculate. By the way, there is one sort of parenthetical remark I would make here, which is these resonances actually have a Lorentzian profile. And if I give you a Lorentzian and I ask you to compute the distribution of the heights, you actually do find this -3/2 power law, which I showed in the previous slide. Okay, so this is the task that we want. And basically this random walk through the ensemble is going to be our sort of crutch to do the calculations. So the way we set it up is basically, and this is sort of the only marginally technical slide that I have. We solve, or we write down the equation of motion for these fictitious dynamics. We have an equation of motion for these eigenvalues, and we have an equation of motion for the eigenstate overlaps, where basically you can see that the correlation between the matrix element and the spectrum sort of manifestly enters. I'm not going to go into the details of how we go about solving this, but we actually can make a lot of analytical progress, and we eventually get a joint distribution. And you notice that in particular, this power law that sits on the top of Z is very different from the -3/2. Actually, this power law exponent depends on the bare Liom characteristic length scale zeta. And the way sort of it comes about operationally is when we solve these equations of motion, we have to put a boundary condition. So the way we choose a boundary condition is to say that imagine I'm looking at two levels, which I know will resonate at some point in lambda. But suppose when they're far from a resonance, at that point, I know that the Liom description is a good description. And I can use the Liom description to compute the matrix elements somewhere over here between the black and the blue levels. So that's why this bare Liom characteristic or Liom length scale enters the result. And then, once I have this Z and distribution of Z and omega, the spectral function is trivial to compute because I can just do the appropriate integrations. And I get a power law which goes as omega to the power minus zeta log 2. And that actually explains why do we have these power laws in the spectral function. So with that, I'll basically conclude. I hope that I sort of very quickly convinced you that the idea is that the MBL phase, these resonances are there all over the ensemble. At these resonances, the eigenstates lose their Liomme character, and then there's basically a wide distribution of the energy scales over which these resonances happen. And basically the sort of umbrella message is that Liommes are a good starting point for describing the MBL phase, but a better and a refined description is to take Liommes plus resonances between them. And with that, I'll finish, and thank you for your attention.
Thank you. We can have some questions.
Would it be possible to include these resonances by enlarging this local integrals of motion by thinking of them as some matrix degrees of freedom locally capturing the cross, the degeneracy of eigenvalues? Is there some way to think of it like that?
Yes and no. So the idea is that, the difficulty is that one could have said that, well, actually what you're showing is that close to a resonance, or if I take a particular disorder realization, which is basically sitting at a particular lambda in this language, then some of your Liommes are not very good descriptions. So why don't you just extend the Liommes to be operators which are spread out over the length scale associated with the resonance and write your theory in terms of that. But the reason that also is slightly tricky is because, so basically imagine that I have a system and there is some length scale R over which the resonance is happening. Now within this region R, the local Hilbert space dimension is 2 to the power R. So there are roughly 2 to the power R levels which sit here, but only 2 of them actually resonate. For the other sort of levels, the Liommes are perfectly good descriptions. So we can't really, as of now, we can't really marry these two to say that, okay, this is the operator which is the right operator to look at. So for some of the levels, the levels that don't resonate, the Liommes are perfectly good descriptions. But for the levels that do resonate, the Liommes are no longer good descriptions. So that's why right now we are at the stage where we say that, yes, it's Liommes, but with resonances. So this is, I don't know if this answers the question, but this is where sort of we are stuck between coming up with a sort of description which I can think of as the operator that sits there and commutes with the Hamiltonian. So that is the.
No, I think I understand a little better now. But if say in that if one had some matrix of size 2 to the R, in which there are isolated points where 2 of the eigenvalues coincide, and then you get a kind of a degeneracy in that subspace. I mean, you could define perhaps integrals of motion which are more matrix integrals of motion, which capture, which reduce to the usual ones, which would be like some traces of the moments of the matrix when they are separated. But when they actually coincide, there might be things that capture the additional, I mean, the fact that there's a degeneracy. You can now have probably you would have additional conserved quantities which are not just the traces of the just the moments.
I see. So basically, you're saying that imagine there is some block structure in this sub Hilbert space, and then you say that one part of the block itself is my integral of motion, and the rest of them are what they were to start with.
Yeah. I mean, you probably seem to want something which, when none of them are coinciding, just reduces to some sum of individual integrals of motion. But when they coincide, you want something which can capture the new additional degrees of freedom which are there in the off-diagonal. Which I think should be possible.
Yeah,
I don't know.
Yes, I think it should be possible, but so the difficulty there is then it becomes quite difficult to write a local description for that, because this is just a cartoon picture for the thing is that there would be overlapping resonances everywhere.
Right.
So that then you can't really write it in terms of a local operator.
No, I can see.
So is there a statement of how these resonances scale with size or something? I mean,
yes. So I sort of swept the system size dependence of all the distributions that I sort of showed. But actually, okay, so since you asked, these distributions, these joint distributions also have something which depends on system size. So there is a system size scaling of these distributions, which comes from the fact that there is a system size scaling of how many resonances can a particular eigenstate or a particular region, both in terms of energy and space, participate in. And then there's a probability of that and so on.
So if it's just extensive, does it just grow with volume, or like
the number of resonances? Yeah, it grows with volume, but there is a small parameter which is this bare localization length zeta, because the theory that I have presented here is works the best deep inside the MBL phase. Because one thing you could have so I thought you can ask that, okay, here I'm focusing on a resonance between this blue and the black level. But then you could have asked that, well, actually, while this resonance is going on, you can see in the background that there are a whole gazillion of levels that are hitting the blue and the black level. So why am I allowed to ignore them? So the reason I'm allowed to ignore them is because there is a certain separation of scales which comes about because of the smallness of zeta. So basically, the distribution over which the resonances happen, the distribution of scales over which the resonances happen, are very, very broad. So that's sort of the content of the other sort of paper I mentioned. So what that means is that this blue level is actually undergoing resonances with many other levels while it is undergoing a resonance with the black one. But some of them are extremely sharp, which corresponds to just relabeling of your Diom levels. And some of them are extremely broad compared to this scale, where you say that, well, over the scale that this resonance happens, you are allowed to say that the state's character doesn't really change. Now, this happens locally for every part. So that's why it's an extensive number of resonances. And coming back to Rajesh's point, that's why I am allowed to, or that's why we could make some analytical progress in computing this distribution, because we said that we can treat these overlapping resonances as independent resonances, because it's very unlikely that a resonance in this part of the system and a resonance on an overlapping part of the system happen on a very similar energy scale. So yeah, that's the argument.
Okay.
Any more questions?
Yeah.
Just a quick question. What is the statistics of the energy eigenvalues?
In which sense? So these are sort of deep in the MBL phase. So modulo some finite size corrections, they are Poissonian. They have Poissonian statistics. But they are not exactly Poissonian. So you have to be very careful in how you take the limit. So of course, in the L going to infinity limit, the eigenvalues have Poissonian statistics. So if I integrate out the Z from this and look at P omega, I would get what I would get from Poisson in the thermodynamic limit. But you cannot put that to compute the joint distribution anymore, because once you take the L going to infinity limit, you can't come back. So you first have to compute the spectral function for a finite size system and then take the L going to infinity limit.
I see. Okay. So should we think of this as an integrable system?
Yes and no. So there is this idea that MBL systems are emergently integrable, because okay, so had this picture been correct, had this picture been completely correct, I would have said that yes, this is an integrable system, because I have, for every site I have a quasi-local integral of motion, and and the number of them is extensive, so it's an emergently integrable. But because this is not the full description, I will not make that statement.
Okay, thanks.
Okay.
Any more questions? If no, we thank Sthitadhi once again.